Alrighty, so yesterday I introduced you to the idea of momentum. Momentum is mass times velocity. So it's defined as inertia in motion. So for something to have momentum, it has to have a mass and it has to actually be moving, right? So like, any of you just sitting there, do you have momentum?
Yes.
No, because you're not moving, right? If you're running down the hall, then you've got momentum. Who's got more momentum running down the hall? Big person or small person? Big person, right? So momentum is kind of, there's two parts to it. It's mass and velocity. If something really small is moving really fast, it's got a lot of momentum, right? So that's the idea. So we will derive the impulse momentum equation from Newton's second law. Probably the easiest formula derivation you've ever seen in your life. Not that you've seen a whole lot, I guess. And I will relate the impulse momentum equation to real life situations, except I won't have the copper pipe to show you. Solve problems using the impulse momentum equation. Now, why do you think I have a golf ball and a golf tee there? What does momentum impulse have to do with golf? Well, you're going to find out right away. Quite a bit, actually. Okay, so again, a bit of a review of momentum. As always, write down as much as you need to. Consider the following examples. We've got a train and a car traveling at the same speed. It would require more force to stop the train than the car. How come? Way more mass. And I think that was you guys I was talking about, especially, right? Yeah. It would require way more force to stop the train than the car. How come? Because of the mass. Another example, a bullet fired from a gun will penetrate a wood block more than a bullet of identical mass thrown by hand. Right? Like if I fire a bullet at a block of wood, it's going to embed in the wood. If I just take a bullet and throw it, even if I'm Will Alidi and I'm throwing a insert miles per hour fastball, well, how many? 50? I think I can throw 50. 87? That's not bad.
Can you read that little recorder thing?
87's.
There's a guy there that handcuffed and throwing him too.
Oh, yeah?
Oh my god.
Was he? And okay, so yeah, as I was saying, as I sort of got on my little rant there, if you just throw a bullet at a wood block, it's not going to penetrate. How come? Not moving fast enough, right? Doesn't have enough momentum. Why are you writing that down? Okay, these two cases are a result of momentum, and as we saw yesterday, this is just review from yesterday. Momentum is the product of the mass of a moving body and its velocity, and the formula is P equals m times v. Why do we use P? Do you remember?
Because the next letter of the alphabet, duh.
Next letter of the alphabet, duh. Exactly. Now, here's the derivation part. You remember this old favorite? A equals delta V over delta T? Mike? Maybe introduced to you in grade 10. Certainly, you should have seen it in grade 11. You couldn't have gotten through the course without seeing it in grade 11, I don't think, anyway. Acceleration is equal to change in velocity over change in time. Remember Newton's law that says F equals ma. Dan, is the A in that one the same as the A in the other one? Yeah, they are. They're not the same font. In fact, here it's not even the same sort of shape of letter, right? But it's the same A. It's the same quantity we're talking about. So we're going to take this. We're going to take this, and we're going to plug it in for A. And what are we going to get? We're going to get F equals m times delta V over delta T. That's step one of the derivation. All right, so all we're going to do is we're going to rearrange this. We're going to take that delta T. So this and you don't need to jot this part down, but I'm just sort of explaining the math here. So it's like m delta V over delta T. Well, how do we get rid of divide by T? Multiply both sides by T, right? So the delta T is going to end up going over there, right? And it's going to cancel here. And so you end up with this thing here, which is F delta T is equal to M delta V. That's put a box around it for me. Just don't freak out. I'm just going to do this so that you can concentrate. Okay? I know. I need you to concentrate. This is commonly known as the impulse momentum equation. Why? The left-hand side is referred to as the impulse, and the right-hand side is referred to as the momentum. M times V, right? Momentum. The product of a force and the time interval during which it acts is called the impulse. Definition. The product of a force and the time interval during which it acts is called the impulse. Can also be referred to as a change in momentum. Now, if P is momentum, then delta P is change in momentum. And usually that's written as, or usually that's analogous to m delta v, right? Mass times change of velocity. If there's a change in velocity, there's going to be a change in the momentum. So delta P, m delta v. This is officially called the impulse momentum equation. I refer to it as fat equals mass. Okay, if you sort of use your imagination a little bit, the little delta sign can kind of become a big capital A, right? And so you get fat equals mass. And that's just, whoops, that's just the way I refer to it. It's not really that. I'm guessing that there's probably no one else in the world that refers to it that way. If you hear me say fat equals mass, that's what I'm talking about. F delta T is equal to m delta V. Okay, so what good is this? I'm now going to talk about relating this to the real world. Since the change in momentum depends on the force and the time that the force acts, right? The change in momentum, the m delta V, depends on or is equal to the force multiplied by the time. If either the force or the time is changed, then the momentum is changed, right? If I apply a bigger force, I push really hard, well, that's going to be a big change in momentum. What if I apply not so hard, but for a longer period of time? You're going to get a bigger change in momentum, right? If the T gets bigger, that's what this next page is all about here, right? If I've got F, let's do this. If the force gets bigger, but the time doesn't, is the mass of an object going to change? Like if you're hitting a baseball, does the mass of the baseball change? No. So if the force gets bigger, for it to be balanced out on the other side of the equation, the momentum or the velocity has to get bigger, which means the ball goes farther, faster and farther, right? If you hit it harder, it's going to go faster and farther. But what if you can't apply any more force? What if somehow you can increase the time that the force is in contact? Well, again, the mass of the baseball doesn't change, and so increasing the time will also increase the change in velocity. How do you increase the time of the force? Well, I know you've been taught this. What do you do when you swing the bat? Follow through. Do you know why? So the bat stays on the ball longer. And this is why. Did you ever know this? This is why? Yeah. By following through, you're increasing the time, right? As you follow through, the ball stays on the bat longer. And by increasing the time, the faster the baseball doesn't change, it's going to go faster, right? That's the whole idea of a bunt, right? When the ball just hits the bat, right, the time is very, very short, doesn't go very far. Okay? So this has some use in sports, baseball, tennis, golf, blow darts. My specially prepared little marker thingy.
And you turn the lights off.
Sure.
Oh.
All right, so let's do the corresponding sample questions.
Did you say that you had a paper crossword?
Oh, I do, yes, thanks.
So we don't have to copy these?
That's correct. Oh, the question, sorry.
My finger hurts. I have so much math homework and I have no idea what I'm doing. It's awesome. You guys have any minutes with
There's actually a
Yeah.
second one of these that is up there. I've actually put the two of them together. I can usually get the marker to go almost entirely to the hole. Good. Let's try it. Okay, so what force will give a 1 kilogram mass a velocity of 4 meters per second in 3 seconds? So we are solving for force. This is the mass. This is the velocity. And this is the time. Now, Fat equals MAV is delta velocity. Is this a change in velocity? What force will give a 1 kilogram mass a velocity of 4 meters per second in 3 seconds? It doesn't say it's initially at rest. It doesn't say VI equals 0. But the way it's worded, it sort of implies that. Don't you agree?
Yeah.
Okay, so this is the change in velocity. It's going from 0 to 4. So it's just F delta T is equal to M delta V. F times 3 is equal to 1 times 4. Oh, this is pretty easy. It's going to be 4 over 3 or 1.3 newtons, right? So easy that it will likely be a multiple choice question on the test. When I say likely, I mean you will. Is that not easy?
Not for multiple choice.
Really? What about multiple choice makes it harder?
And you actually have to like do it. No, but like very
All right, let's try another one. Maybe this will be harder. I don't know. A 10 Newton force acts on a 2 kilogram mass for 5 seconds. Find the impulse. Now, I've told you already that the impulse is that left side, that F delta T, right? But I haven't actually told you what impulse, like what's the formula. The correct sort of letter for impulse is, want to guess?
J. J.
It is J.
Oh.
Why?
Oh.
I don't know. I is current in electricity. I don't know. I don't make these rules up.
We're gonna run out of letters so we can go by the
There is only 26 of them yet. J is impulse, and that's equal to the F delta T portion. So it's a 10 Newton force. Oh, but it's on a 2 kilogram mass.
Oh.
Oh, but for 5 seconds.
Oh.
So I got my time, right? So what's the force? 10 times 5, 50. Now, I haven't come up and said what the unit for impulse is, have I?
There is none.
It would, well, F is newtons, T is seconds, so it's in fact Newton seconds. Impulse is in Newton seconds.
AKA Bennett.
No, Bennett's is only, no, you can't have Bennett's standing for multiple units. No. That is a definite no. You don't have to put the dot, is that what you're asking? You don't have to, but yeah, but you'll see it both ways, either n dot s or ns. But it's not newtons per second, it's newtons times seconds. Yeah. Find the delta P.
That was like great falling. I'm like, what?
Okay, well, delta P is equal to, don't write this down yet, m delta V, but I don't have the velocity. How else can I find? Yeah, well, basically, it's the fat math. Right? You've already got the impulse portion. It is 50.
I can't read your writing. Yeah, true. Sorry.
Okay, that's why I try and speak what I'm saying here. So I'm just going to go fat math. Fat F delta T is equal to m delta V. And the fat part is 50. We just calculated that. And the mass is 2. So we're going to solve for delta V. And this has to be automatic, you guys. There can be no, right? So it's going to be 25 meters per second. Oh, I think I kind of went too far here, didn't I? I got distracted by something. Because I was only supposed to find the delta P, right? So what is delta P? I'm going to write it over here. Delta P is simply 50, right? Because F delta T is equal to M delta V. The impulse and the change of momentum are the same thing. Now, is there a unit for change of momentum? It's kilogram meters per second. So the impulse and the change of momentum are one and the same. In fact, Newton seconds are equivalent to kilogram meters per second.
So if they're the same, is it possible for them to be the same?
I was like,
Is that all?
No, when one side is changed, the other one must also change. Right? Give and take, like bargaining. Yeah. So that means that therefore this tells us then that if the delta V is 25, then therefore the final momentum or final velocity is 25. Okay.
just did it.
Well, I kind of got ahead of myself a bit over here, didn't I? I'm gonna go to emergency one of these days. Think. Okay, do you want to try this one on your own? Have some confidence. How much time will it take? Solve for time. Will it take to slow a 5 kilogram body? So that's the mass. Moving at 20. Oh, we're going from 20 to 5. VI and VF kind of thing, right? And the braking force is 10 newtons. So we're solving for time. We're solving for time. So the first thing I should do is probably this, I guess, right? I'll try not to get ahead of myself. 5 minus, is this okay if it's minus 15?
Yes, slowing down.
Slowing down? Technically, I guess that's meters per second. What's that? You're going to need a negative something else, exactly. So now this goes over into F delta T is equal to M delta V. The force is 10. The mass was 5 minus 15. 5 times 15, 30, 60, 75. Going to divide by 10, right? And I get minus 7.5 seconds. Just put a plus and just say, eh. Yeah?
Get rid of the plus or change your 10 to a minus.
That is actually what you should do, right? Because the force is in the same direction as the change in velocity. So if it's slowing down, then that means that the force is sort of like opposite to the motion, right? So that should technically be a negative 10 because it's a negative force, right? You should never have negative time. I sort of throw that in there just as a reminder that if you got negative time, it likely means, well, there's either it could be as small as that, or you've done something really wrong, right? 7.5 seconds. Does that make sense? Yeah. Are these relatively easy? Yeah.
Yeah, but just wait.
Oh, well, there'll be more for sure. But but wait, there's more. For only the low cost of nothing, I'll be happy to teach you two-dimensional momentum collisions.
Tomorrow.
Right, on Monday?
Yeah, later.
You gotta go drop that ball.
Oh yeah. Well, we still got to do some problems.